All right, let's see where we left off here. Well, yeah, we got done talking about how can we figure out that two hyperreal numbers are on the same level. So for hyperreal numbers, x and y are on the same level if their ratio equals some real positive number. Clearly, y does not equal 0. Also, again, you could take their ratio in any way. Maybe this equals some t in element of the real number, positive reals. So what do we mean by that? So, for example, let's take x to be 2 omega and y to be 6 omega. All right. Notice that when we take their ratio, we get 2 omega over 6 omega. But the omegas cancel, so we get 1 over 3. So that's an element of the positive reals. So that's how we can prove that they're on the same level. Okay. Here's another example. What about 3 omega plus omega squared versus, let's call this our x, versus 12 omega. Notice if we take their ratio, 3 omega plus omega squared divided by 12 omega, we can factor out an omega from the top, and we get 3 plus omega in the numerator, and we get a omega times 12 in the denominator. The omegas can cancel, so then it ends up being a 3 plus omega divided by 12. So bringing this calculation over here, we notice that, maybe down here, we notice that 3 plus omega divided by 12 can actually approximate, is that how we want to argue it? We can do it through approximation, but we can also, so first I'll do it by approximation in orange, then I'll do it through algebra in white. So via approximation, the numerator approximates to 3, the denominator approximates to 12, so we get 1 over 4. Algebraically speaking, we can distribute the 12 to the numerator over here, and we can distribute the 12 like so as well. Then you can say, by definition of omega being on a lower level than 12, this term becomes 0. Then decomposes to the same result, 1/4. So in both ways, it's the same thing, just looking at it a different way. So what if the ratio was flipped? You know, I just arbitrarily picked one to be x, one to be y. What if I switch it? What if I have 12 omega divided by this omega squared plus 3 omega? What if I have this? Well, notice again, the omegas can cancel through factoring, because over here we can factor out an omega, and we still get omega plus 3. Cancel. This ends up as 12 over omega plus 3 which then we can do approximation, say that this is 12 over 3, which then equals 4. But they're both positive real numbers. 4 and 1 over 4 are both positive real numbers. So they both render the same result. 1/4 and 4 are both positive real numbers. They both satisfy this definition of two hyperreal numbers being on the same level. Okay. So let's do some more approximation examples. So what does 497 plus 5 omega approximate to? What is this approximately? Why?
Because it's the highest level.
Yeah. It's higher than omega. So compared to 5 omega, this is basically 0 compared to 497. Let's do another one. What about 3 omega plus 1,000,000? What does this approximate to? 1,000,000, that's a lot, huh?
Mm-hmm.
Why are you shaking your head?
Because it's not a lot.
Compared to 3 omega, would you rather have $1 million or 3 capital omega dollars? 3 capital omega dollars? Yeah, you wouldn't have to work a day in your life anymore if you had 3 capital omega. But in today's day and age,
People would know that.
even with $1 million, you can blow through that pretty quick. I mean, $1 million. I mean, that doesn't even get you a Bugatti Veyron these days. I think those are like 2.5 or maybe 3.5 million. Wow.
We can get you a nice little Tesla.
It's probably a better engineered car. Okay, so we get this. Probably can't go as fast though. So what about 2 omega squared plus 3 omega cubed minus 15 omega minus omega squared plus 13 omega to the 3/2. What does this approximate to?
Three omega cubed.
Mm-hmm. Why?
It's the highest level.
There we go. So you guys are getting this concept. This concept is important. Okay, that's why we're beating this dead horse. So let's talk about the approximation principle. This says that if in your approximation, if the result of an approximation is 0, the approximation was performed incorrectly. More on this as we move along. So, for instance, this is what this approximation principle is talking about. Let's say we have something like 2 plus omega quantity squared minus 4. one might be able to assume that, hey, doesn't this equal approximately just 2 squared minus a 4? Which then equals 4 minus a 4, which then equals 0, right? The approximation principle says that you made an error here because your approximation led to a 0. Here's why we don't let it equal 0. It's because when we're doing arithmetic with these infinitely small and infinitely large numbers, what we want is to have non-trivial results, okay? So to avoid a non-trivial result like a 0, we want to treat this omega as a very tiny number, but nevertheless not so insignificant in our theoretical development that we could just toss it away. So correctly, what we would do is we would expand this like so. And notice that this becomes 4 plus 2 omega plus 2 omega plus omega squared minus a 4. 4's cancel. These add, so we get 4 omega plus omega squared. Now, what? Now we can approximate, because we could say, compared to here, this is on a what level compared to here? This is on a higher level?
Oh, no.
Yeah, you got to make sure
Yeah.
it's lowercase. When lowercase, if this was capital omega, you'd be right. But it's lowercase omega, so it's the opposite of that. Higher powers here mean lower level. So this is on a lower level. So this can actually approximate now to 4 omega. This is what we mean by we want to have non-trivial results. That's a trivial result when it equals 0. It's a non-trivial result when we can extract some information out of it, even though it's infinitesimal. Over there, we would have no information. Over here, we have some information. It's not just some omega. This difference between these two quantities is not just nothing. It ends up being something, even though it's really small. Over here, we would have assumed that it would be nothing, and so there's no information extracted. But it's as if we theoretically zoom in further to get more information. I don't see any, like, I don't see any cells when I look at my arm, but for sure we know our skin is made out of cells, right? Let's do another one where we invoke the approximation principle. 3 plus omega quantity squared minus 9. Here's how you don't do this. You don't say, oh, well, that's compared to 3, that's like nothing. So this becomes 3 squared minus 9, which is equal to 0, right? And that's what you don't do because of the approximation principle. It says the result of an approximation, if it equals 0, then it was done incorrectly. According to this theoretical framework that we're trying to establish. We're trying to establish a theoretical framework, such that we actually extract some type of tangible quantities out of our approximations. So first, what we'll do is we'll expand this. Then we'll do the algebra here. So this becomes 9 plus 3 omega plus 3 omega. Omega squared minus a 9. 9's cancel, so we're left with 6 omega plus omega squared. Now let's approximate. What does it approximate to? Very good. Notice again, we've extracted some tangible information out of it. Whereas before, we were just going to say it's 0. Not so fast. This is because Yeah, well, you'll see more. This is just such a beautiful situation here, because notice that 3 plus omega is truly approximately just 3. So this should be true. This is true. But so is this. They're both true. It just depends on how you look at it, right? We want to look at it like this because it's more interesting. We can extract more information out of it. So let's use approximations with fractions. What about this one? We got 2 plus omega. 2 plus square root of omega. How do we do this one? Well, you have to approximate the numerator and the denominator separately. Okay, so let's do it. How will we approximate this numerator here? 2. Don't just jump straight to 2. Let's work level by level, right? Why don't we? So working level by level, what do we get? Two plus omega, right? Because omega squared compared to omega and 2 is tiny in comparison. Over here, it's just 6, right? Then we do it again. And yes, you are correct that you assume that this happens. But doing it level by level is good practice. Secondly, it shows you don't have to jump straight to this step. You have this step to entertain as well. Okay. So what about capital omega squared plus 3 divided by 2 omega plus omega to the 4th? What does this give us? Approximate the numerator and the denominator respectively. What do we get in the numerator? Mm-hmm. What about in the denominator? Hmm?
2 omega.
Mm-hmm. Now what?
Wouldn't that just be capital omega squared? Or no?
Say what?
I said, would that be just capital omega squared? Or you would just leave it like that?
No, you don't just leave it like that. You have, when you're mixing capital omegas and little omegas, you always have to go back to the definition that 1 over little omega is equal to this capital omega, and vice versa. 1 over capital omega is equal to this little omega. So
if you have a capital omega is equal to 1.
yeah, notice that this is the same thing as omega squared over 2 times 1 over omega. Is it not? So then what does that 1 over omega turn into?
Capital.
Yes. So then a capital omega times a capital omega to the second gives us a capital omega to the what? So this is our final result. So we want it all in terms of one kind of omega, if you will. One more example and then we'll move on. What about 6 plus 7 omega squared divided by 2 plus the square root of omega? What does the numerator approximate to? What does the denominator approximate to?
2.
Yes. So then this does equal 3. So now we get a theorem. Let x be approximately y. And let x1 be approximately y1, where x1, x2, where x1, y1, x and y, they're all hyperreal numbers. Okay? There's two statements in this theorem. That x1 is approximately y1. And here's the other statement. That x over your x1 is approximately your y over y1. Where x1 and y1 don't equal 0. Let's prove this. To prove this, I need more space here. Here's part A. Suppose x equals 0. And you guys won't have to do proofs for your homework or your tests. These proofs just demonstrate why these are true. It's important in part of the theoretical development. So if some of the stuff doesn't make sense, it doesn't make sense why we're flowing the way we're flowing, then it's just try and appreciate it for what it's worth. I hope you guys learn what it's talking about, but it isn't fully necessary for the spectrum of this course. When you take higher and higher levels of mathematics, knowing how to prove stuff is very important. So this gives you an introduction to that. So if x is equal to 0, that implies y is equal to 0. Because we're in this situation right here. We're in situation A, where we're saying x1, x. We want to show that this is approximately y1, y. Okay. So if we suppose x is 0, this was 0. So 0 times anything is 0. So we're saying 0 should be approximately what? Well, 0 is only approximately itself. And since 0 is only approximately 0, that means what was on the right-hand side is approximately 0. So because we've assumed y1 and x1 aren't 0, the only culprit that could cause this to become 0 is y. Therefore, that's why that implies y is 0. Because y1 is non-zero, and the product of two numbers resulting in the value of 0 means that one of them had to be 0. And via that assumption over there, it's y. So in this case, if x is equal to 0, this implies that this is established. Part A has been established. So what about if x is non-zero? Which is the more interesting case, which is more difficult case. By hypothesis, we have that x is approximately y, and that x1 is approximately y1. Do we not? So that means they're on the same level. These two are on the same level. These are on the same level, and these are on the same level. So what does that mean? Well, it means when you take their ratio, and I want to take the ratio that we want, let's say y over x. Why do I take y over x? Okay. This renders a real value, a real positive value. So that means it's on the real level. So that means that they're on the same level. So now we talk about this expression. Where does that come from? Well, recall by definition, we discussed this definition last class. X being approximately equal to y implies that you get y minus x all over x. That this ratio renders a real result. Okay, so when we take this expression, we get y on the left right here, y1 on the left, x1 on the right here, and then x1 on the denominator. It's just by definition of approximate for two hyperreal numbers to be approximately equal. So notice here's some mathematical trickery being involved. That this is the same thing as y1 minus yx1 plus yx1 minus x1 all over what you had originally xx1. Why is that true? Well, it's because these could cancel. This is the negative of that. So just putting this just as an overcomplicated version of that. I could just cancel these out and go back to this equation. But I'm not. We're doing this for a reason. So what happens if we factor something special out of these guys? Let's say I want to factor out a y. Okay, what if I want to factor out a y from these guys? And what if I want to factor out an x1 out of these guys? So what does that give us? That gives us y times y1 minus x1 plus x1 times y minus 1. And over here I said x1, and it needed to be x1 minus x1. So then this is not a 1, this is a x. Everything divided by x1. Then we can distribute this x1 to both pieces of the numerator. Okay, so then we notice that the x1's cancel here. And what do we get once we combine this y over this x? We get y over x here times this y1 minus x1 divided by x1 over here, plus this y minus x all over x over here. So, what's all this about? Well, we notice that this renders a real result. That's what level this is on, remember? Because we said that X and Y were on the same level because they're approximately the same. What does this result in? Is it a real? Does this end up being a real number?
Yes. Well,
Remember, these two are on the same level, right? If they're approximately the same. So if I subtract two things that are approximately the same in the numerator, what does the numerator end up becoming? So what if I say, what's 3.0001 minus 3? They're approximately the same, right? What does this end up becoming? A very small number, right? Whenever you take two numbers that are approximately the same and subtract them from each other, the result is their tiny difference that their difference. So same here, y1 and x1 are approximately the same, and they're hyperreal numbers. So they're very small, and they're very close to each other. So their difference is basically zero, almost zero. So this result is infinitesimal. INFT. Writing out infinitesimal takes a lot of effort. INFT, infinitesimal. And then, what about here? Recall the same argument applies. X and Y are hyperreal numbers that are approximately equal. So then this also ends up becoming an infinitesimal. So we have a real number times the infinitesimal plus the infinitesimal. A real number times the infinitesimal itself becomes a what? Infinitesimal. Remember? Day one. We talked about that, how a real number times an infinitesimal number becomes an infinitesimal number. Their product becomes an infinitesimal number. So this is an infinitesimal plus an infinitesimal, which leads to what? When you add two infinitesimals, you should get what? An infinitesimal. So our result equals infinitesimal. So this is infinitesimal. You remember what that means by the definition? By definition of two infinitesimal numbers being approximate, if this ratio is equal to 0 or infinitesimal, that implies that they truly are approximate. Because we were trying to show this. This was not taken as given. That's why it's called a proof. We're trying to prove that this is true. We did not assume it was true. We showed it was true. We took this ratio right here, changed it up algebraically a little bit, factored, and showed that it ends up being an infinitesimal plus an infinitesimal, which results in an infinitesimal. So by definition, this has been verified. So now we move on to part B. Let's verify this one. Again, you guys will only be expected to use this. You won't be expected to prove it. Now, proofs may be bonus points on exams. That's always fair game. Because I want to encourage you to learn this stuff on this level. I want you guys to learn this stuff on this level. I can't force you to, but I can provide incentives. Can I not? I could provide incentives for you guys to learn it on a deeper level. And I will. So I'll make bonus questions where you have to prove stuff. Let's prove part B. We want to show that this is true. Okay. So it suffices to show that this is true first. Why? Oh, because we could just use part A. We could just use part A to finish it off. If we show it to this point, we can use part A, something that we've already proved, to finish it off. Because then it just suffices to show this. Because once you've shown that, if this is true, then x times 1 over x1 should be approximately y times 1 over y1, which clearly this is what we want to show. This being true because this is true. Because if you assume this is equivalent to this, or not equivalent, but approximate, and this is approximate to this, then the product of what was on the left-hand side together and the product of what was on the right-hand side together, they should be approximate. Same thing here, if you establish this is approximate to that, and by hypothesis, you know this is approximate to that, then their product on the left and the right should be approximate. Okay? So it suffices to show this. So this is what we want to show first. This is how we're going to attack the problem. We want to show that that is true. So to show that this is true by definition, x being approximate to y implied that y minus x over x is 0 or infinitesimal. So over here, applying it to this, we want to show that 1 over y1 minus 1 over x1 all over 1 over x1 is either 0 or infinitesimal. That's what we want to show, that it is either 0 or infinitesimal. Okay. Notice that multiplying by reciprocals, we end up getting that x1 over 1 is multiplied by this. Okay, so notice that the x1 travels across each of them. Notice that x1 over x1 is what? Yes. So what's going on here? Notice that we can now multiply top and bottom here by y1 to have them have the same common denominator. So then I get x1 minus y1 all over y1 when we combine them under the same denominator. So we started off with this, and it's become this. And what is this? Yes! Why did you say that?
Because you said it.
No. Why is this infinitesimal?
Because if they're approximately the same, then if you subtract both of them, you get an infinitesimally small number.
In the numerator, yes. And that, compared to the bottom level, is much lower. So if you have something on a lower level in the numerator and a fraction, the overall fraction decomposes to an infinitesimal. So we've done it. We've proven that this is true. Because again, remember, we were trying to show that it equals 0 or infinitesimal. And we've done it. So we've established this to be true. And so it follows from part A that if this is true, that this is true. Uh-oh. By this argument here. So we're done. What you guys need to know is that you guys can just use these. If you have x is approximate to y, x1 is approximate to y1, and they're hyperreal numbers, then you can do this. Now that we've proven it, you have earned the right, and that you sat through it and helped with it, you have earned the right to be able to use the theorem. People shouldn't be allowed to use theorems unless they proved it. Right? That's kind of like saying people shouldn't be allowed to drive cars unless they made the car themselves, right? Very few people would drive cars then, right? Only mechanical engineers and other people would only be able to drive cars. What we've done is we've allowed society to use the theorems we've invented without them knowing how it works. But there's a price to pay for that. The price to pay is people don't appreciate it. Not only do they not appreciate it, but they don't understand it either. Which I would say it's even worse than not appreciating it. At least understand it. So let's approximate this. So how do we approximate this? Well, we'll approximate what's inside the radicals first. What is this approximately? 9. What is this approximately? 4. So this is approximately plus or minus 3 minus plus or minus 2. Well, we'll take the principal square root. So this becomes 3 minus 2. This is 1. What about something like this? What does this approximate to? Well, the numerator approximates to what? So what does that give us? So what does that give us? So what does that give us? Not 6, but 0. Is that okay? Not by the what? That says this is a no-no. We don't want that. That's a trivial result. We want a non-trivial result. That means we need to be able to extract more information out of this situation than we did when we did this. How are we going to do that? We're going to do it using algebra. We're going to do it using an algebraic operation called the conjugate. We're going to multiply top and bottom by the conjugate. Okay. When you do that, you end up getting middle terms cancel, and you get this, and the bottom becomes omega square root of 9 plus omega plus 3. Don't forget the parentheses, because the little omega has to distribute to both terms. The top is what happens when you foiled, if you will. I don't like to call it FOIL, but you foiled this binomial times that binomial. The reason this ends up happening is because you get a square root 9 plus omega times itself. You get itself. The middle terms cancel, and then negative 3 times positive 3 gives us this. Yes, then they cancel. Then we get this. Hence why I didn't put the omega through. Because now the omegas cancel. And we get this. Now what happens when we approximate this? 1 over what?
6.
1 over 6. How are you getting that? Are you approximating this to be 9?
Yes.
And then you're square rooting 9 and you're getting 3 and you're adding it to 3. So 3 plus 3 is 6. Yes. What's going on here? First, we approximated it to be 0. Now we're approximating it to be 1/6. Do you see how different that is? And really, we didn't do anything different besides algebraic manipulations. So that's crazy. That's really cool. We were able to extract more information using the approximation principle. It allows us to actually tap into the true power of these infinitely small numbers, because it allows us to escape division by 0 or trivial results like equaling 0. Really cool. That information wasn't accessible until we figured out how to access it. This is what you call a new discovery. This is a new discovery. Mathematicians have discovered this, and so have we now. It's really cool. So now let's talk about absolute value approximations. So let's first talk about the definition of the absolute value. Let's define piecewise as being x if x is greater than or equal to 0, and negative x if x is less than 0. This definition is why the absolute value of -3 is +3, because absolute value of -3 would then be -3, because x is less than 0. We put a negative on it. That's why the negatives cancel to give us +3. And clearly, absolute value of +3 would just be 3, which is just 3. That negative is what makes them positive definite. So, what is this?
Negative omega plus omega cube.
No. No omega cubes involved.
Or omega squared.
Here's a better question. Is it positive, negative? What is this? Greater than or less than or equal
Omega plus omega squared.
to omega plus omega squared? No.
No?
Wouldn't it be, it go negative omega into another, negative, into the negative omega into a positive omega. So it'll be,
You said negative like 8 times. Are you saying it's a negative or a positive?
Would it just be the same thing?
This omega squared term has a negative on it.
mhm,
This omega term doesn't.
yeah.
Which one is on a higher level? this one. Therefore, this is positive or negative? That's what I wanted to hear. So when we take the absolute value of a positive number by the absolute value definition, this is just equal to this. But you have to tell me why. If you don't tell me why, then you can't say that that's true. Because if it were negative, which it's not, but if it were negative, then it should equal this, which then equals this. It's not, but if it were, that's what you have to do. So this absolute value equals this. And this approximates to this, right? On the first level approximation. On the second level approximation, it would go to 0, right? It just kind of depends. Depends. You're learning how to use this tool. I may have to give you an extension on this homework for 1.2 because we're still on the approximation section. We're almost done, but we've actually hit the time limit. So let's see here. Let me see. When is the homework due? Let's go to assignments. Homework 2 for 1.2. I'm saying it's due on the 27th. You should be given a week to complete it. And although we're almost done, I would say I want to give you guys some more time to do it. So instead of it being due this following Wednesday, I'm going to extend the due date to this following Friday. So a week from today. So we're not fully done with 1.2. There's just a few more examples about it with the absolute value that I want to talk about. So then on Monday, once we do that, we'll move into 1.3. But I want to give you guys some more time because I want you guys to learn this stuff thoroughly. So I will change the due date. How about that? Sound good? You get 2 more days to do it. Yeah. It's also on Canvas. If you go on assignments, it's there. If you click on homework 2, it says due date 1/29 now. Okay. You people watching at home, thanks for randomly sometimes talking through the matrix. That's okay to do.
How do we give you the homework for the
1 second.
for
Say
this
it.
one?
Hold on, I can't hear you. Hold up. Say it louder.
How do we give you the homework for today?
You're gonna have to take pictures of it. Don't use
And email it to you.
Don't use Cam Scanner. Take JPEG pictures, attach them to an email, and email them to me.
All right.
And
Okay.
I'll expect them to be due before, like, by the end of class. Your colleagues are turning it in now, so I'm expecting the email now.
All right. Okay. Thank you.
I sent my email before class started.
You did what?
I sent my email of the homework before class started.
Okay, that's fine.
Awesome.
Thank you. Have a good one. You too. Yeah. Good job. Talk to you guys later.